Alright, this is our last video before we change gears completely and start talking about chemical kinetics. In this video we're going to investigate some of the factors that influence solubility. Alright, so an incredibly useful concept when we're thinking about solubility is the idea of like dissolves like. And what this means is substances that have a particular type of intermolecular forces like to dissolve in solvents that have similar intermolecular forces. So, a solute that can undergo hydrogen bonding would rather dissolve in a solvent that can participate in hydrogen bonding rather than something that is nonpolar and only has dispersion forces. Or a more general way to think about it is polar things and ionic things tend to like to dissolve in polar solvents, and nonpolar things tend to like to dissolve in nonpolar solvents. And so if we took pentane, sorry, didn't mean to move that. If we took pentane, C5H12, and tried to mix that with water, because pentane has London dispersion forces, and water can undergo hydrogen bonding, these are very different intermolecular forces, and so a nonpolar substance like pentane is not going to want to mix with a polar substance like water. It turns out this is incredibly useful to chemists, and a lot of the different lab techniques that we use and forms of chromatography that allow us to separate substances take advantage of this idea of like dissolves like, and that nonpolar things and polar things tend not to like to mix or interact with one another. Alright, so this slide kind of harkens back to the solution energetics that we talked about in a previous video, but if the intermolecular forces between the solute and the solvent are greater than the intermolecular forces in the pure substances, that is going to allow us to form a solution because it's going to be energetically favorable. And because it's mixing, it's going to be entropically favorable. And so when this is true, we'll always get a solution to form. If the intermolecular forces in the solution are similar to the intermolecular forces in the pure substances, then the solution will also form, because now if the energies are basically the same, then that process is going to be governed by the entropy, and so that will always favor mixing, and we'll get a solution to form. And then if the intermolecular interactions between the solute and solvent are weaker than the intermolecular forces in the pure substances, then we may or may not get a solution, right? And so in this case, we have a competition between the enthalpy, which in this case wouldn't favor solution formation, and the entropy, which would. And so solutes tend to dissolve in solvents with similar intermolecular forces, because then we're going to, at the very least, be in this category, if not this one. If the intermolecular forces are very different, then the mixing is less likely to happen. Alright, so as an example, we want to decide if each one of these compounds is more soluble in hexane, which has the formula C6H14, or water. And then in each case, we want to determine the solute. So what intermolecular forces exist in the pure solute? What intermolecular forces exist in the pure solvent? We would call that the solvent-solvent interaction. And then what intermolecular forces exist in the mixture? What are the intermolecular forces that exist between the solute and the solvent? And so if we have naphthalene, both naphthalene and hexane are nonpolar. And we know that because carbon-hydrogen bonds are nonpolar. So we don't even need to worry about, like I just gave you the formula for the hexane, but you don't even know what the geometry is because we know it's going to be nonpolar. So it will only have London dispersion forces. And so this nonpolar naphthalene is going to be more soluble in hexane. It's not going to want to dissolve in the very polar water. And so the solute interactions, so that would be the interactions in the pure naphthalene, that's going to be dispersion forces. The solvent interactions, so that's going to be for hexane. That's again going to be London dispersion forces, and then because these are both nonpolar, all of the intermolecular forces in a mixture of naphthalene and hexane will be London dispersion forces. Right, formaldehyde, now we have a molecule with polar bonds. The carbon-oxygen bond is polar, and it's asymmetric. So formaldehyde is polar, and so then we would expect it to dissolve in water. Now the solute-solute interactions. So formaldehyde is polar, but we don't have a hydrogen directly connected to that oxygen, so it can't undergo hydrogen bonding. So the solute-solute interactions are going to be dipole-dipole. The solvent-solvent interactions, so that's saying what would be the intermolecular forces in a sample of water. Well, two water molecules can hydrogen bond with each other, so that would be H bonding. And then the solute-solvent interactions. Right, remember that for hydrogen bonding, they both have to be polar. Both molecules have to contain oxygen, nitrogen, or fluorine, but only one of them has to have a hydrogen directly connected to an oxygen, nitrogen, or fluorine. So water meets the more strict criteria for hydrogen bonding, and then formaldehyde, because it's polar and it has an oxygen, meets the second weaker criteria for the second molecule. So when water interacts with formaldehyde, that would be hydrogen bonding as well. So naphthalene is going to be more soluble in hexane in all of the interactions. Solute, solute, solvent, solvent, and solute, solvent are going to be dispersion forces. Formaldehyde is going to be more soluble in water. The solute-solute interactions are dipole-dipole. Solvent-solvent interactions are hydrogen bonding. And the solute-solvent interactions will also be hydrogen bonding. All right, our last example on this slide is stearic acid there on the bottom. So I'm going to erase this stuff to give us a little bit cleaner slide. And while I'm at it, why don't I move this up? So stearic acid I picked on purpose because it gets us to an interesting point, right? This region of the molecule, we would say, oh, that's clearly polar, right? I've got two oxygens, these polar bonds with the between the carbon and oxygen, also this oxygen and the hydrogen. It's not symmetrical, so this region of the molecule is very polar. And so we would probably expect that to dissolve in water. But then I have this giant region of the molecule that only contains carbons and hydrogens, and so that region of the molecule is nonpolar. And so this is actually a difficult question to answer. And it kind of depends on, once the nonpolar part gets big enough, that will dominate and the molecule will be more soluble in hexane. If we had a much smaller nonpolar part, then this would dominate and it would be more soluble in water. And so I won't give you a molecule like this on a quiz and ask you to answer the question, but I picked it more importantly because this shows that when we get big molecules, especially those of you that are biologists, you're dealing with proteins. Those are enormous molecules. They may have polar regions that want to interact with water and non-polar regions that want to interact with other non-polar things. So for small molecules, it's an easy question. Is it more soluble in water or hexane? When we get to bigger things, it's much less black and white, and there's certain gray area. We can have both polar and non-polar regions of the molecule. Another important application of this, besides biology and proteins and amino acids and whatnot, is soap. So this molecule, stearic acid, is typical of molecules you would find in soap because they have a polar region that will allow it to dissolve in water, but then it also has a non-polar region that will be attracted to the grease and oils and other non-polar things on your body and pull them away. And so this will stick to the greasy, oily molecules. This will stick to the water to allow you to wash those non-polar things away. All right, so this is kind of a terminology slide, but a concept as well. Solubility. That is a term that we use for the maximum amount of solute that we can dissolve in a given amount of solvent. And this slide is all kinds of messed up. We should insert here the maximum, and of course this should be solvent. Right? We know that we can dissolve a lot of sodium chloride, table salt, in water, but there's a limit. Once you reach the solubility of sodium chloride, you can't dissolve any more salt in that solution, and that solute will just collect at the bottom of the beaker or whatever it is that you're mixing them in. And then another term that we have is saturated solution. So a saturated solution is one in which the maximum amount of solute has been dissolved. And so a saturated solution is one where we can't dissolve any more solute at that particular temperature. And if you have a saturated solution where you have some undissolved solute in the bottom of the beaker, then that system will exist in dynamic equilibrium. This is just like vapor pressure that we talked about in a previous chapter. If I have a beaker with water and it's saturated with sodium chloride, we will have a process where as new molecules of sodium chloride dissolve and dissociate into ions, ions that were already dissolved will reprecipitate. And so if you have a saturated solution with undissolved solute present, this is another example of a case where we'll have dynamic equilibrium, right? The total amount of sodium chloride dissolved in the solution won't change, but it doesn't mean that no change is happening. It's just that new NaCl's are dissolving at the same rate that other NaCl's are reprecipitating. All right, when we consider solutions where the solute is a solid and the solvent is a liquid, one of the most important factors influencing the solubility is temperature. And so what this chart represents is the temperature on the x-axis and the solubility of various substances is given on the y-axis. And so each curve represents the maximum amount of each solute you can dissolve in water at a given temperature. And so as we go across on the x-axis, the temperature is increasing. And if you notice, for most solids, the solubility increases as we increase the temperature. It's not true for all substances. You can see specifically sodium sulfate, the solubility decreases as we increase the temperature. But you probably know this from your everyday experience. If you try to dissolve sugar in hot tea, it tends to dissolve very readily. And if you have a glass of iced tea and you try to dissolve sugar in it, it generally requires much more work, much more stirring to get the same quantity of sugar dissolved. So it dissolves more easily, but also in hot tea, we can dissolve more sugar than we could in cold iced tea. All right, so the major factor influencing the solubility of solids is temperature. For gases, they tend to the solubility of a gas and liquid tends to depend on both the temperature and the pressure. So you have probably experienced the temperature effect of gases in your everyday lives, right? If it's July and you leave a bottle of Coke in your car, and it gets hot and you come back, right? You're probably not eager to open it right away because you know it's gonna foam over and spray stuff everywhere. And that's because at higher temperatures, the solubility of gases decreases. And so when you have that hot Coke, all that carbon dioxide that's dissolved in the water, once you release the pressure by opening the cap, it all wants to come out of solution at once and your beverage fizzes over. Cold sodas don't tend to fizz up as much because the carbon dioxide is more soluble at that temperature and it doesn't come out as readily. And if we think about what's happening in chemistry terms, in order for the gas to remain dissolved, it has to be trapped by the intermolecular forces between the gas molecules and the solvent molecules. As we increase the temperature, the gas is more likely to be able to escape the strength of those intermolecular forces and leave the solution. Now, because the volume of solids and liquids don't change very much, pressure tends not to have much of an effect on the solubility of solids in liquids. It does, but it's relatively small and we often ignore it. But for gases, because the volume of a gas is very dependent on the pressure, pressure does have a strong impact on the solubility of gases. And if we think about sodas again, we can think about what the effect of pressure on solubility is. Right? At higher pressures, if we push down on the gas, we can force it into solution. And so, your cans of soda are canned under relatively high pressure to get that CO2 to go in there. But as soon as you pop the can and release that pressure and let it come to the system come to a lower pressure, now gas escapes and you see bubbles forming in your soda, because as we've decreased the pressure, now the gas is less soluble, and so it'll form bubbles and it will leave your solution.